Hi, this video is going to walk you through a chi-square test of homogeneity. So a chi-square test is conducted to test for homogeneity or to see if there's the same count in each category. So that means with one variable, the expected matrix has each cell count equal to the grand total divided by the number of categories. So we're going to use the following example. So it says babies are born every day. So a person might assume that birthdays are evenly distributed. Now it says to survey the class. Unfortunately, we can't do that. So we're going to use the data from 7th period AP Stats. Now in 7th period, there's 26 students. So if I wanted to find the expected number, I would take my total number of students, 26, and divide by 4, because there's 4 seasons, winter, spring, summer, and fall. So I would expect 6.5 students to be born in each season. Now, you might be thinking that that's not possible. I can't have half a student born in a season, and I completely agree. But with our expected number, we want to just leave it as a decimal, even if it does not make sense. Now, the actual data for 7th period is 5 students are born in winter, 8 in spring, 6 in summer, and then 7 in fall. Make sure that it does actually add up to 26. Now below our table here, it says if the expected cell counts are greater than or equal to 5, use your data above. If not, use the data below instead. So if I'm looking at those expected, this is one of our conditions that we're going to talk about in just a minute. But each of those cells has to be above 5 or equal to 5. And because it is in this case, we're going to stick with this data. So the next part here is my actual assumptions or conditions. I'm going to go ahead and pause the video for just a minute and write out my conditions, and then we'll talk about those. Okay, so we have 3 conditions for our chi-square test. The first one is counted data. So in this case, we are counting the number of students born in each season. So I would just put number of students. The second condition was random and independent sample. So we can suppose that students were selected randomly, and additionally, I would assume that birthdays are independent of each other. And then my last condition is the expected cells are greater than or equal to 5. Now, because my lowest is 6.5, that condition has been met. So all 3 conditions we can check off. Next up is our hypotheses. Again, I'm going to pause for just a minute and write out my null and alternative hypotheses and give you a chance to write your conditions down. Okay, so you're going to notice that our null and our alternative hypothesis are a little different than usual. So my null hypothesis, I would state that births are evenly distributed across seasons. And if you remember from our very first introduction to this example, we started by saying babies are born every day, so a person might assume that birthdays are evenly distributed or the same number in each season. So that's what I started off by assuming. And I want to show that births are not evenly distributed across seasons. Now for the actual mechanics. So let's go ahead and say that alpha is 0.05 in this case. And to calculate our degrees of freedom, so it's the number of categories minus 1. So because I have 4 seasons, I have 3 degrees of freedom. And then for my actual test statistic, so our chi-square test statistic, remember the formula is the sum of the observed minus the expected squared divided by the expected. So I'm going to pause for just a second here and write these components out. Okay, so now that I've substituted in the values, let's talk about what we see here. So each component consists of the observed minus the expected to see how far away it is, squared to obtain a positive value, and then divided by the expected. So kind of similar to our z-score formula as well. So I added each of those in for the observed. You can notice those all in red, 5, 8, 6, and 7. And then I calculated each component individually and took the sum. So for my final chi-squared test statistic, it'd be chi-squared equals 0.768. Now, if there's 3, 4 components, it's not too bad to write this all out. But if there's a lot more components than this, I would not expect you to write all of these out. So one way that you can shorthand this, kind of like when we did probability, is if you look over here. So I included the formula. We always need to have the formula. Then I set up the first component plus ... plus the last component. So this would be one way to kind of show your work, but you do not have to write out every single component. Now, if you do not already have your calculator and pink sheet out ready to go, please pause for a moment and get those out. So we're going to talk about how we finally come up with our conclusion. So remember, our curve looks a little bit different, okay? So our curve is going to be skewed to the right. And just to get a kind of an idea of how this would look, so our mean, because it's right skewed, is drawn towards the tail, and it's the degrees of freedom. So my mean would be about 3, and my chi-squared test statistic of 0.768 is going to be roughly over here. So to come up with our conclusion, there's a few ways we could do this. One way would be to look up the p-value. So on your calculator, if you go to second vars, number 8 is chi-squared CDF. So I want to select chi-squared CDF. My lower bound was 0.768. My upper bound is a ridiculously large number. And then I had 3 degrees of freedom. Shoot. Sorry about that. Let me go back here. So second vars, number 8. Here we go. Okay, so I get a p-value of 0.8577. So the probability that chi-squared is greater than 0.768, 3 degrees of freedom, is 0.857. Now, as you can see, that is an extremely large p-value. But if you go back and look at the original table and comparing the actual observed number of birthdays with what we expected, they were all pretty close. So we shouldn't be surprised that we have an extremely large p-value. So typically, just like we have been, I would start my conclusion off by saying with a p-value greater than alpha equals 0.05, I fail to reject H0. I have no reason to believe that birthdays are not evenly distributed across months. Okay, the last thing I want to show you is how you would do a test in your calculator. So if you go to Stat, Test, I'm going to actually arrow up because I want to get to D, chi-squared goodness of fit. So notice here it says observed L1, expected L2. So that's where I need to put those observed and expected. So I'm going to quit out of here, go back to Stat Edit. So in my first column, I'm going to type in the observed. So we had 5, 8, 6, and 7. And then in L2, I'm going to put the expected. So 6.5 for each. So now I can go back to stat, test, and we're going to do chi-squared goodness of fit. So observed L1, expected L2, and then I need to enter in my degrees of freedom, so 3. And if we go down to calculate, here it gives me my chi-squared test statistic of 0.769, my p-value of 0.857, and then my degrees of freedom. So that would be extremely useful if you have many categories, whereas we just had 4, so it wasn't too bad. Okay, please now go on to try the first practice problem on the worksheet handed out.